So, yesterday we went over multiple type of titration calculations in general because we're heading into the section of acid base where we're not just doing general calculations for strong acid, strong base, weak acid, and weak base. Now we're going to start putting it into the context of diagramming the entire journey of a titration experiment. Okay, but we want to do a quick challenge problem that address the last type of titration problem where you find percent purity. And normally percent purity is calculated by grams, but sometimes you have complicated dilutions. And so sometimes you do percent purity by molarity, especially when you have a diluted sample that you're trying to find the purity of. So for this problem, out of curiosity, did anyone, okay, how about this? Joy, what did you get for the percent purity? 92 point what? Yes. Okay. So excellent. So you pretty much follow similar step process where you go through and you write your balanced chemical equation because you got to know, you just got to know, okay, the stoichiometric molar ratios. All right. So it's 2HCl combines with SrOH2, which apparently is this textbook author's favorite compound. Strontium hydroxide, and it goes to, okay, SrCl2 and 2H2O. All right. And you, of course, find the moles required for neutralization. Oh, of course, find the moles required for neutralization. So you're given the titrant information. So you find that the moles of titrant, which is, by the way, our acid, is going to be equal to 4.112 times 10 to the negative third moles. Okay, I don't want to do all the math because this should be rote at this point. You should be able to easily get to moles given molarity and volume. Then you're going to figure out the moles of pure strontium hydroxide that was neutralized. Because impure strontium hydroxide means it's not going to be neutralized because it's not strontium hydroxide. So you're going to find the mole value of pure strontium hydroxide. And for here, you have to keep in mind that you have a 1:2 ratio, stoichiometrically speaking, of neutralization of acid to base. So you're going to find that the value is half the mole value of the acid. So it's 2.056 times 10 to the negative 3 moles of base, pure base, were neutralized. Then what you're going to do is you're given, okay, the respective dilution values. So instead of trying to dilute and then calculate to grams, you could just calculate the molarities of the respective impure versus pure sample of SrO2, OH2, and then compare the percentage, right? So put pure molarity over impure molarity. So what you do then is you say, well, pure SrOH2 is equal to 2.056 times 10 to the negative third moles per. I was told that I titrated, let's see, 25 portion neutralized. So 25 milliliters, 0.025 liters. And that's going to get me a pure molarity of 0.08224 molarity. Okay, what about impure? Well, in the beginning, I had a 2.70 gram sample diluted to 250. So I just use my molar mass, turn it to moles, and then divide by liters, and I get my impure molarity.
Sorry, I have to help somebody with their homework. Here's that.
Oh, I wasn't. Yeah, thank you. I appreciate it.
Here's some.
Okay. You really do want me to die, don't you? So then I do 2.70 grams, multiply it by the molar mass. Okay. 121.6 grams. And then I divide it essentially by the dilution volume, which was 0.025. 0.2500 liters. And I get my impure molarity to be 0.08882 molarity. And then all I do is I do percent purity by molarity because I don't want to have to do the whole, like you're basically doing a similar amount of work because you could have converted the molarity to grams, but it's kind of just easier because we do want to account for the dilution. So you'd be doing an extra step to go back to grams. Okay. So what we do is percent purity by molarity for this diluted challenge problem. And we get a value of 92.6%, which is exactly what Joy got, which is exactly correct. So this is a common type of FRQ problem where the AP takes something that you know to be true. You know the process, and they add one aspect that asks you to reconsider how that affects the process. How do you account for a dilution in a percent purity problem that is rather a straightforward calculation? How would you account for that information in the prompt? Number one trick to AP questions, okay? Read the question part first before you read all of the prompt, because not every single piece of information relates to every single question. It often relates to portions. But then you get problems like this, where it's like, no, everything matters. I have to account for it all. Understanding where you're trying to go will help you determine what you need to account for in the prompt. It also just takes practice. The more exposure you have to AP problems, the more you start seeing the patterns of questions they write for you. So, and I can't go over every single type of problem they're going to give you. Yes. The part that's neutralized is the pure part, because impure things can't be neutralized properly. It'd be like, it's like saying impure means it's mixed with something else. Like there's a different compound present. So that part isn't going to be neutralized by the HCl. So, any other question?
So basically what you're saying is that not all of the 2.7 gram sample is actually SR.
Exactly. Exactly. So, okay, let's move on. We're going to talk about strong acid, strong base titration, a strong to a strong. And we're going to actually quantitatively, okay, describe each stage of a titration. Okay, so we're going to take all this mathematical knowledge and now plug it in to defining each section in the titration. FYI, there are pretty much no practice problems I wrote in here in terms of where you do one step and I do one thing and then you do the exact same. We're going to just shove you straight into the workbook and the AP question quizzes online. So here we go. So let's talk about titration curves between strong and strong, which is the simplest articulation of titration. Okay, why? Well, with a strong acid, strong base reaction, you always produce a salt and a water. Because basically acid bases are double displacement reactions in a sense. Okay, especially when it comes to strong and strong. If you are asked to demonstrate the net ionic equation, by the way, which is a super common AP MCQ. What's the net ionic equation for this process? It would look like this. It would be H3O plus or H plus combines with OH minus to produce 2H2O. That would be the net ionic equation because what it does is it focuses on the acid base interaction. The spectator ions, which is revealed to form the ionic compound, which then dissociates, okay, in water is non-relevant, irrelevant, okay? And what we get is depending on whether you're titrating via strong acid into a strong base or you're titrating a strong base into a strong acid, you get these two respective curves, okay? When you look at these curves, just use common sense. If it starts at a low pH, you know that your sample is starting as an acid and you're putting in more base if it goes to a higher pH. The vice versa is true. It's always really sad to see when those types of points are lost. okay? By the way, the shape of the curve before in these beginning stages will become very important as we progress. It is very important to note the standard titration curve for a strong base, strong acid, or flip it, strong acid, strong base. That first portion of the curve, how it looks, is going to become incredibly significant to us when we start comparing weak acid or weak base titrations, okay? So here I'm going to create like a little chart to kind of summarize the 4 stages that we can calculate in a titration problem. And the first is before equivalence. Okay, what you're going to notice is this first half of the table is going to be the conceptual understanding. This second half is going to be the math for finding the pH that goes with it. Okay, so this is how I'm breaking down my summary tables. So before equivalence, if you're starting with a strong acid, and this would obviously be the exact opposite for a strong base, okay? But let's say I'm going from the acid perspective. So this is going to be, we're doing a strong acid. We're doing a strong acid analyte with a base titrant is what I'm going to depict in this table, okay? Boom, for this table. Before equivalence, we know that pH is 100% way less than 7. It's super acidic because of the high concentration of strong acid. So that means you can straight up just use pH equals negative log this to find the pH value, which means you can also find the concentration of the acid, right? The next stage that we get to that we often are asked to calculate is, well, we're heading toward equivalence. That's like where we care about. At equivalence is neutralization, right? It's the point of neutralization. But we can also calculate halfway to equivalence. And what we notice is that conceptually, we're seeing a gradual, okay, increase in pH, right? But pH is still less than 7 because the acid is still more dominant. It's still the dominant species, especially when you think about titrating. It's drop by drop. You aren't getting anywhere super fast. At least you shouldn't be. Okay. But FYI, when you return from break, one of the first things you will do is a titration lab. Yay. So, and then what we would do is we would have to figure out the excess. To find the pH, we have to do excess math. My small amounts of base that I add are being neutralized by the acid. So my pH is going to be determined by the remaining acid that hasn't been neutralized at this stage of the titration. So, let's see. Do you want me to go through the table first and then the math, or do you want me to go through the math as I go through each stage of the table? Table first. You got it. You got it, dude. Full house. Anyone? Nope. You're too young. Okay. So, we'll do this problem. This will be the sample problem below. Okay. Next, you hit equivalence, which is in the end goal of acid base. We want to hit equivalence because that reveals the molarity of the analyte. That is our neutralization point. So we know then that the moles of acid are stoichiometrically equivalent to the moles of base. Okay, that's what we're looking at. And we know for strong acid, strong base only, we always get a pH of 7 at neutralization. So there are AP questions where they're like, can you determine the pH of a problem between this strong acid, this strong base? You don't have to do a single ounce math. You can literally just say, it's a strong acid, strong base. I know it's going to be 7. Okay. So, and then we can actually calculate pass equivalence. Now, pass equivalence, you've neutralized all of your acid, right? So you know then pass equivalence, you're going to have a pH greater than 7. Greater than 7 because now you have excess OH minus. And you would do an excess problem, okay? Just from the OH perspective. So it's a similar process, just now you're trying to figure out, okay, how many moles of extra base that I add determine the POH and use the relationship between POH and pH to find the overall pH of the solution that would obviously be greater, significantly greater than 7. These are the most straightforward of them. Okay, so there is going to be a new table I introduce here because notice strong acid, strong base reactions are never in equilibrium. They're not in equilibrium. So we're not going to use an ICE table to determine the change. We're going to use what we call an ICF table. It's initial change final. That helps us determine the excess. Equilibrium is initial change at equilibrium. That's the only difference. But this is a new table. Okay, so it represents the final concentration for reaction that goes to completion, but is not in equilibrium, okay? So for this problem, stage 1 of our summary table, let's calculate the pH before equivalence, okay? So I actually, we're not gonna do that. pH halfway to equivalent. You don't need a calculate. Sorry, we're just gonna do. You should be able to do this. We're not doing a practice problem. This is like no dir, sir. You do this. Like literally, it's a no dir, sir. Okay. You can do that. If I give you the concentration, you should be able to find the pH. Yay, thank you. So we're gonna move on to halfway to equivalence. That's the problem that we actually want to go through. And this is where we find the excess H plus given the amount of base that we added that has completely been neutralized by the acid analyte. So what we do here for this one is we are told, okay, that we want to calculate the pH. Given the fact that we added 12.5 milliliters of 0.1 molar strong sodium hydroxide base to 25.00 milliliters of 0.1 molar HCl. Now, your first question might actually be, wait, how do I know it's halfway? It's not to equivalence yet. You could just calculate what would be necessary in mole amount to get to equiv. And if you notice it does, both of them don't meet it, then you know you're not there yet. So that's just something to keep in mind. Kevin, do you need to stand up at a lab station? Okay, that's just a trick that all my kids did last year. So what you're going to do is, first and foremost, you're going to do the same step as calculate molarity after dilution, right? We did mix them, so we need to figure out our new molarities. So what we have here is HCl diluted molarity is equal to 0.1 molarity times, well, I was in a 25 millisable, but I got diluted down to 37.5 when I sum up the volumes. So it gets me a concentration of 0.06 on repeat molarity. Okay, then I need to calculate, okay, well, what's the molarity of my NaOH? Okay. And what I get is that I started off at a 0.1 molarity times 12.5 milliliters that has been diluted down to 37.5 milliliters. And I get a value of 0.03 on repeat molarity. Now, I'm not going straight to moles quite yet because part of the reason is I want to end up in molarity anyway of acid present to plug into pH. So I'm just kind of keeping things in molarity for right now. It's also going to fit better in an ICF table, which is very similar to an ICE table where we use the molarity values. Okay. And then what I do is now I plug into my ICF table. So to do that, you write the one direction equation. There's no equilibrium. It's a solid line. So you write the equation out and it's HCl to NaOH goes to NaCl and H2O. Okay. And you write ICF, initial change final. Okay. Now, of course, we don't do anything with the liquid because that's not important. Okay. So what we notice is, well, we're in the beginning stages. So that means what I need to figure out is who do I run out of first? because that's going to help me determine what my final concentrations are after these things react. So what I realize is that since I am before equivalence, my limiting reactant at this stage of titration is my base, obviously. I'm completely still dominated by my acid. So what you're going to do now is you're going to plug in your concentrations and you're going to say, well, if I start with initially in the mixture, my diluted samples of 0.06 on repeat and 0.03, and I know I have no NaCl left. What I know is that whatever is left in excess means that I used up all of my NaOH. So what then the change become is I've used up all of my NaOH, leaving me 0. Because I'm still dominated by my acid. Okay, I haven't neutralized all of my base yet. Otherwise, I'd be at equiv. And this is stoichiometrically going to change my acid by 0.03 on repeat as well. And it's going to add 0.03 of the salt, whose ion concentration is that molarity dissociated in water. And what I get then is I get the final value for the acid, my excess acid, to be 0.03 on repeat. And I'll actually change the color. Okay, 0.03 on repeat and 0.03, which by the way, I don't really care about in the end, but I'm just filling in the table. Okay, and so what this tells me is it tells me what's my excess concentration. So this is, you could do it the other way I taught you with excess, but this table actually wraps, I think it's actually easier to plug it into the table. Okay, and you're not doing all these moles back to molarity dilution conversions. You're just keeping it at molarity, accounting for dilution, plugging in, knowing that, hey, if I'm before equiv, I know that whatever base I used is completely used up, and I just need to figure out how much acid is left stoichiometrically speaking. And then what I do is I take that value and I simply plug in for pH. Okay, is equal to my negative log of HCl excess. And I get that I have a pH of 1.477 because I simply just plug this in. All right. Okay. So I didn't include practice problems for this because I'm just going to shove you straight into the workbook at the end of class. All right. But are there any questions so far on the process? You could do it the other way. I think the table lays it out really nicely. You could do that. There was a reason in the textbook that I remember reading it. I'm like, that was a really good reason to use these ICF tables. But part of it is because of the stoichiometric thing. You can see the stoichiometric changes. So it also helps you catch that if you had a polyprotic strong acid. Yeah.
So did you put negative 0.03 for concentration of NaOH because the eggs that you have equal 0?
Exactly. I put it as negative because I know that it's being neutralized and used up completely. Because every drop I add, it's still not enough to completely use up all the acid, but all the base is being used up that I add slowly.
So if it's limited, then you just do opposite.
Yeah, you use it all up, so you get rid of it. The change is it being consumed. Yep. Okay, so that's calculating pH halfway to equiv. Again, before equiv, it's just please plug in the molarity. Just like plug it into your negative log. That's it. You got it. Okay. So at equivalence, you do it. I don't really feel like I need to go over this, so you do this one at equiv. So welcome back. So for this problem, you totally should be able to prove conceptually that you reach equivalence. Okay. But you also could have taken the conceptual route of, for a strong acid, strong base, when you've reached equivalence, which by the way, you aren't often given a problem that says, I've reached equivalence. You're given a problem. Here are the amounts. You have to figure out did you reach equivalence based on the mole value of acid and base? And then what you could have done is you don't have to do any more math after that. If your moles of acid stoichiometrically equaling moles of base for a strong acid, strong base titration, you literally could just written pH is what? Exactly. Now, your mathematical proof would be determining your diluted concentrations of HCl, which you should have gotten 0.05 molarity, and your diluted concentration of NaOH, which you should have gotten 0.05 molarity. And if you wrote out the reaction as we did above, okay, here, you know it's a 1-to-1 ratio necessary for neutralization. So you know that if you have stoichiometrically, okay, 1-to-1 molarity, you've reached, and they're equal, you've reached neutralization. Therefore, you can say pH is 7 for the solution because you are have attained neutralization. And that would be your mathematical proof above. Reach equivalence or neutralization point. That was it. So for the next problem, now you're calculating pH beyond equivalence. And I want you to do this because you can do it on your own. It's just the opposite of what we did in the beginning before equivalence. So go ahead and try this one on your own. And I offered a different version where you don't use the ICF table. You could just use the other version that we know. I'm showing you both ways that you could do it. So go ahead and do this one on your. Let's talk about this one. Let's talk about it. So past equivalence, you're now just looking for excess OH. You're definitely getting, when you're talking about a strong base being titrated into a strong acid, obviously all of this will flip for a strong base, strong acid titration. Similar steps, flip it, okay? But for calculating beyond equiv, okay, all you had to do was find, okay, the diluted values, okay, and you should have found for HCl diluted that it's 0.04545 molarity. For NaOH diluted, you get 0.5 0.05454 molarity. And what you find then is that because NaOH produces a 1-to-1 ratio of OH minus, the molarity of the NaOH is the molarity of the base. So this is equivalent to the base, okay? And that HCl is equivalent to the H plus because it is a 1-to-1 ratio of ion production. Okay, it is, it is equivalent to H plus. So then you simply put this into the excess, okay, equation that you know that you're going to have excess OH minus, and it's going to equal H plus U. Okay, OH minus H plus, and you should have gotten a value of around 0.00909 molarity excess. Okay, then you simply use this equation pH, because I'm asking for pH, not POH. And right now the information I have is in terms of base. So I'm going to use this relationship pH equals 14 minus POH. And what I do is when I plug all of that in, I get 11.959 to 3 sig figs. Okay, because it's 3 sig figs after the decimal. And that is my pH post equivalence given this specific amount of excess base added. And that is the end of titrations for strong acid, strong base. Please remember, if you are reversing the process, you're titrating a basic solution, you're titrating a basic solution with acid, you would have to consider these relationships and you would just reverse everything. But that being said, okay, what you should do now is you guys have a couple videos. You have an AP question video, which forces you to go in and start looking at these types of problems. You also have a buffers intro lecture, because tomorrow we're going to start hitting up weak acid, strong base titrations, and then Friday, weak base, strong acid titrations. And FYI, we go from being able to calculate 4 regions in a titration with a strong to strong to now 6 regions of calculations for a week. So that is why we started off with strong. All right, guys, best of luck. And those of you at home, bye.